All right, so today we'll talk about electric charges and fields. Okay, you know two kinds of charged particles, protons and electrons. Okay, and we'll talk about them. Okay. So the next four chapters is about electrostatics. Okay, we'll take a bunch of charges, okay, and see what is happening around them. But these charges won't be moving. So everything we talk about, these charges will be addressed. So that's the next four chapters. And then, once we're done with this, then we'll get the charges to move. Okay, so that's the natural progression. So you guys, a lot of you guys know what happens. If you have two positive charges, what do?
They repel.
Yeah, they repel each other. A positive and a negative charge will attract each other. Okay. Now here's an interesting thing. So this was only found about 100 years ago. Mr. Millikan found this. That you go out and find any charged particle. A cloud is charged, and then it'll discharge. And what you find is you can test any cloud. The smallest charge you see is E, and we'll come to that in a second. So this is minus E. And if a cloud is charged, what you find is the charge is N times E. You can't go to a store and buy half an E. Yeah. So charge is quantized. And Mr. Millikan discovered this about 100 years ago. Okay? So we'll talk about all of that. All right, so here's another story that we'll talk about in this chapter. Okay, this guy, what does he do? He repels him. If he repels him with a force of 10 pounds, what does this guy do to him? Down, I guess, and that's Newton's third law. Okay. This guy repels him there. What if we put this guy in Palm Coast? Will he still feel the force?
Significantly less.
Yeah, so, but he'll still feel the force. What about if we put him in New York?
Even less.
Even less, but he'll still feel the force. So how does he act upon it at a distance?
It's exponential.
Yeah, no. I can't push you from here. Right, so to explain that, what you do is we have the story. And the story goes, okay, so the story goes, what this guy does is, well, he'll create an electric field all around him. Okay, and to put words to your claim, the electric field denoted by E gets weaker further out you go. And this guy in Palm Coast is feeling the electric field right there. He doesn't care what created it. All he's doing is responding to his local condition. Okay? So that's the story. So those are the 2 points being made in this chapter. Okay? We'll talk about, we'll give you an expression for the magnitude of the electric field. This is a vector field. What does that mean? It is a field of vectors. At every location, there's a magnitude and direction. Okay? The magnitude of the vector is given by K, a constant, Coulomb's constant, times the charge producing the field. Stronger the charge, stronger the field, divided by R squared. R is the distance at which you're calculating the electric field. What is the direction of the electric field? It points radially away from the point charge. If this is a point positive charge, it points away. And if it's a negative charge, which way will the electric field point toward it? Okay, so for a negative charge, the field will point towards it. All right? So we'll talk about all of that stuff. All right, so the next 4 chapters are electrostatics. We'll talk about charges at rest, and then we'll get the charges to move. All right, yep.
Is it still cool if I take the test?
Right now?
Yeah.
All right. We have a 3-minute pause in the recording.
Sorry.
Come on.
What's that?
Hey,
Last lab, we measured harmonic resonance on a string with a weight on it. And that was it. It wasn't that bad. It was nothing, yeah, nothing that we've learned, since this new semester started. It was literally the last section, last semester.
So in our everyday experience, a lot of charge is generated by friction. You rub one object against another, and the friction will transfer charges. Okay. You've experienced this when you walk across a carpeted floor. When you walk across a carpeted floor, charge will transfer from carpet to your shoes and so on. And in the winter, you can get yourself a shock by touching a metal object. Okay? So what this chart shows is when you rub these materials against this material, these guys will give up electrons, one of their outermost electrons, to these guys. Okay? So these guys don't hang on to their electrons too tightly, and these guys like electrons. Okay, so if you rub acrylic or polyurethane rod with a silk cloth, the silk will become positive and this rod will become negative. You rub wool against rubber, electrons get transferred from wool to rubber. Okay. So here's a rubber balloon. Yep. So there you go. Here this illustrates an attractive force between opposite charges and a repulsive force between like charges. Okay. Okay, so like charges repel each other, unlike charges attract each other. So we are talking about electrical insulators and conductors, okay? And generally, good electrical conductors are good thermal conductors as well. But what is the difference between electrical conductors and... So example of an insulator is a piece of wood. Example of a conductor is a piece of metal, okay? So what is the difference between the two?
Insulators, electricity doesn't like going through,
Yeah.
whereas conductors will readily.
Yeah. Well, I wanted a little more than that, but
In insulators, the electrons aren't able to freely move between the different atoms.
yeah, so there are no free charges in insulators. Yeah, so this is a conductor. And this is an insulator. Yeah. And there are no free charges there. And, okay, so you learn insulator. You will learn later, 4 chapters from now, when you connect a battery, what the battery does is it establishes an electric field, okay, in the material. And in an insulator, there are no free charges to respond to the electric field. In a conductor, you have an electric field, and you learn that these electrons will start moving in the opposite direction. Okay, so you need free charges for an electric current to flow. Yep. So that's a conductor. And in a conductor, what is happening is, all right. So let's make copper, okay, a copper wire. So here's a copper atom. A copper atom is neutral. And what we'll do is, so copper, the atomic number is 29. I don't know if I want to get in there. Okay. 2 electrons in this shell, 8 electrons, oops. Eight there. Okay, I'm not 100% sure about this, but
It's 18, and there's 1 in the last valence shell, which is why it's such a good conductor.
this is 8.
It's 18 plus 3D.
Um,
The 3D shell is full of copper, so it's 18 on that ring.
in the P shell, there's 6s, 8, 3s, 3p. is 2D, no, there's no 2D. 3S, 3P.
The 3D10 on this last one.
Okay, so that's 8, 18, and we still need,
One.
no, copper is 29.
18 plus 10 is 28, leaving 1. Unless I'm mistaken.
Yeah, no, this is 2, 10, 18, and we still need 11. All right, so 8 and then, okay, 3P, no, this is 3P and 3S. 3D is 10. Yeah, 3D is 10, and 1 electron there. That is 4S. So this copper is willing to give up this electron easily. Okay. So here's what happens. When you assemble a bunch of these copper atoms, okay, all these copper atoms want to go in the lowest energy state. And they can go in the lowest energy state by giving up one of the electrons, or one or more. They become positively charged. Okay? And so they live in a sea of freely moving electrons. Okay? And that's a low configuration. That's what happens in most conductors. Okay? And so now if you look at these electrons, they are in a band. So this is all a occupied band. This is and this is called the conduction band. So you need a partially full conduction band for it to be a conductor. Okay. If this band is full, then that would be an insulator. It won't conduct electricity. Okay? So in an insulator, the conduction band is empty. This is called the valence band. Okay? And to make a good conductor, you need a partially full valence band. Okay? All right, so electrical conductors have free charges that can respond to an electric field established in there. Insulators have no free charges. Semiconductors have in-between stuff. Okay? And what you can do is in semiconductors, you can control the number of free charges by adding impurities during manufacturing. Also, in semiconductors, the number of charges can be increased with temperature. Okay, so the conductivity of semiconductors varies. But anyway, their conductivity is in between that of conductors and insulators. Okay? So they have desirable properties under various circumstances. Okay? So the number of free charges can be changed with impurities. This is during manufacturing. And the more impurities you add, the more free charges it'll have. Okay? As well as temperature. We won't worry about this. Okay, Mr. Coulomb measured this force between charges law. Okay, and we call it the Coulomb's law. And he used this equipment. Okay, so what Mr. Coulomb found out was between two charges, if the distances are, the magnitude of this force, so if the charges are like, they'll repel each other. The magnitude of this force is given by this formula. K, now we call it the Coulomb's constant, a constant times the product of the charges divided by distance squared, the distance between them squared. Okay. And K, the Coulomb's constant, is 9 times 10 to the 9 in SI units. So what we're talking about is the electric force or the electrostatic force. This is enormous compared to the gravitational force. Okay. So what these two examples give you is the force in the hydrogen atom. Here's a hydrogen atom. Okay. The attractive, so there's two kinds of forces acting here. There's the force of gravity, because they both have masses, the proton and the electron, and the electrostatic force. They're both charged particles. And in a hydrogen atom, this guy is enormous compared to that. And the electrostatic force divided by the gravitational force is 10 to the power of 39. That's 1,000 trillion times greater. So what we're saying is when this guy is talking, you can ignore him. Okay? So when the electrostatic force is in play, you can ignore gravity unless it's yeah. Here's another example. Okay. All right, can you hold up your bottle, water bottle? So that's a liter of water. You fill that with water. Thank you. And strip it of all its electrons. So you have 1 kg of proton is what you have, roughly. It's really about half a kg, but we won't get into the details. And you take another kg of protons. They will repel each other. And they're 1 meter apart. The repulsive force will be equal to the weight of the Earth. So that's how large the force will be. Take one of those glasses, one of those water bottles, hold them that far apart, the repulsive force will equal the weight of the Earth. All right. So in nature, when you have a thundercloud and stuff like that, in a thundercloud, charges separate. Okay. Again, just like when you're walking across the carpet, the friction separates charges. In the turbulence created in the cloud separates charges. Okay, so you get charges separated, and you see nature doesn't like charges too much of the charge to build up. What happens? You have intercloud lightning, and this charge discharges, neutralizes via lightning. Okay. All right, the superposition principle. So let's say you have multiple charges. You ask the question, what is the force on this guy? Well, here's how you find the force on this guy. Calculate the force due to this guy, which is that. That's a vector. Calculate the force due to this guy, which is that. And the net force is just the sum of these two vectors. Okay, so this, what the superposition principle essentially is saying is the following. When you're calculating this force, the effect of this guy is ignored, or the effect of this guy is independent of the effect of that guy. Okay. So that's the superposition principle. You can have a million charges. You can have as many charges as you want. To calculate the effect on this guy, you calculate the effect due to each of these guys, and then add up the vectors. Okay. Okay, in nature, there are only 4 fundamental forces. The strong force, the electromagnetic weak, and the weak force, the electromagnetic force, and the gravitational force. So you studied this in physics 1, now you're studying this. Okay. To study these two, you generally have to go to grad school, physics grad school. All right, but now we can understand some stuff, fairly important fact. Okay, so let's build we'll build a lithium atom. A lithium atom has Okay, now you just learned that like two positive charges will repel each other. Do you guys know the size of an atom? Okay. The size of a nucleus is 10 to the minus 15 meters. Okay, to give you a scale, this is not a scale drawing at all. So if I really wanted to draw the nucleus on this scale, it would barely be a point. Okay, so to give you a better picture, if this was the size of a football stadium, the nucleus would be the size of a marble at the center. Okay. So that's how big the atom is compared to this. Now the reason I'm mentioning this is, look at this. In this tiny object, here are two positive charges. They don't like to be next to each other. What are they doing? They're repelling each other like crazy. So my question to you is, why aren't they flying apart? Why aren't protons shooting out of the nuclei in your body?
There's a stronger force holding it together.
Yeah, so, and that's what this is. Okay? See, this force is 100 times stronger than that. Okay. So, the strong force is 100 times stronger than the electrostatic force. Now the deal is, this strong force only comes into play at those distances and less, at 10 to the minus 15 meters. Okay? And now you understand why all nuclei have to be that size. If you want to build a nucleus, they have to be that size. Okay? So you got to bring them that close enough where the strong force takes over. And because the strong force is so binding, okay, you can release a lot more energy when you put together a nucleus. You know, 1,000,000 times more energy than when you burn stuff. Yeah. All right, so this table gives you the relative strength of the force. If the strong force were 1 unit big, the electromagnetic force is 100 times weaker. The weak force is 1,000,000 times weaker. And the gravitational force is enormously weaker. Okay? 1,000,000 trillion times weaker. This gives you the range. Gravity has an infinite range, so does the electromagnetic force. The weak force has a range smaller than the strong force. The strong force has a range of 10 to the minus 15 meters. This is 10 minus 18 meters. Okay. When you learn to describe forces using quantum field theory, what you learn is the forces are mediated by particles. The strong force is mediated by gluons. The weak force is mediated by these particles. These are bosons. And the range is determined by the mass of these guys. The heavier these particles, the smaller the range. If you have a range of infinity, that means the mediating particle is massless. Okay, so these are the four forces that we experience. Okay, so this was the Big Bang. And so this is 10 to the minus, this is about 10 to the minus 43 seconds after the Big Bang. 10 to the minus 43 seconds. Okay. So, all right. We'll take H2O. You guys all know what H2O is. Okay, I have H2O at 200 degrees Celsius. What is the physical form of H2O? steam. Okay? And then I'm going to cool it. Okay? I'm going to cool it to 90 degrees Celsius. Now what do I have? I'm sorry?
Water.
Yeah, water and water vapor. Okay? So, you see, at lower energy, this separated into two phases. Okay, we'll go still lower.
Ice.
You can have ice, water, and vapor. Okay, so at even lower temperatures correspond to lower energies. The same stuff can separate into different phases. And that's what we believe happens for forces. At very high energies, it was one force. That one force separated into different forces, into the four forces that we see today. At these energies, at the energies that we live in and that we experience, you see that as four different forces. At extremely high energies, at the energies that involved near the Big Bang, at those temperatures, above that temperature, all the four forces were a single force. That's the belief. Okay? So that's what that thing is saying. So properties of charges, charge is conserved. What does that mean?
It's just like heat. They cannot be created or destroyed. It
Yeah.
changes.
So the total charge of the universe is constant. Yeah? Charge is quantized. So if you go to a store and buy, no matter what charge you buy, you find that you're getting n times the smallest charge. And the smallest charge is the charge of the electron, and it's 1.67 times 10 to the minus 19 coulombs. Okay? So the electron is negatively charged, and the proton is positively charged. Okay. Now here's another amazing thing about the electron. See, here's the electron, 1.66. Oh, 2. But all right, here's the amazing thing about electrons. See, the proton is 2,000 times heavier than the electron. The proton is made of quarks, and the electron is a fundamental particle. The proton is made of 3 quarks. The electron is a fundamental particle. This guy's 2,000 times heavier than that guy. Totally different guys. But their charge is exactly the same. To as many decimal places as you want. Okay, so this is the measured value. And how do we know that? All right, you go outside, grab a handful of dirt that has many, many protons and many, many electrons. And it's always neutral, no matter how big a clump of earth you pick up. Okay? So Mr. Milken did this experiment a little over 100 years ago, and he found that the charge was quantized. He found the fact that, so what he did was he squirted oil drops. That's why it's called the oil drop experiment. And no matter how much charge you gave the oil drop, the charge on it was always Q times NE. E was the smallest charge found on it. Okay, so here was the experiment. So he'd squirt oil drops, and some of them would fall through this thing. And as they're falling, they would reach terminal velocity. Like if you have a skydiver, you jump off a plane, you'll reach terminal velocity. And the terminal velocity is related to the mass of the oil drop. Okay? So he would squirt oil drops, watch them, measure the terminal velocity, and he knows the mass of the oil drop. Now, what he would do is he would shine X-rays which would ionize the air. Some of the charges would get charged, oil drops would get charged, and he would turn on an electric field. And if he turns on an electric field like this, the oil drop feels an electric force like that. Hi. And here is the force of gravity. Okay. And he would adjust the electric field such that this force was equal to that force. Okay. What is the electric force? The electric force is equal to mg. The electric force is Q times E. And M, okay. What is M? Mass of what? The oil drop. He found that from the terminal velocity. He knows the electric field from the voltage applied. Okay. G we know. So Q he could measure. He did this for millions of drops, and what he found was it was always Q was always N times. Yeah. So charge was quantized. That's what he found. Okay. Shows shining X-rays in the lower chamber ionizes the air. Some of these charges attached to the oil drop. Anyway, so he found, Mr. Millikan found Q is always N times E. Okay. You guys can, there's a nice YouTube video on this thing, or you can find it. There's plenty of nice YouTube videos on this experiment. That experiment won him a Nobel Prize back in the day. All right, so here is a more immediate application, an electrostatic precipitator. Do you guys know what this thing does? Yeah. So here's a thermal power plant, let's say. What is a thermal power plant? I'm sorry? Yeah, so here we're burning coal to make, yeah, and then running a turbine and producing electricity. All right, so here this is smoke. If you're living here, you have chronic respiratory illnesses. Okay. So how do we fix that? We don't want that. Okay, so here's what we do. So these are metal plates, okay? And these are wires. So here's a metal plate, here's a metal plate, and this is a wire, okay? What we're going to do is we're going to connect 25,000 volts between this and that, okay? Or more. Yeah, so let's start off with 25,000 volts. Okay, what this wire does is it'll spit out electrons. Okay, if you have a high voltage, it'll spit out electrons. Now we'll pass smoke through here. Smoke is a bunch of particles, carbon, soot, and all that. Okay, well, carbon particles will be flowing through there. What do those electrons do? They attach to the soot particles. Now the soot particles have become negatively charged. What do? They attract to the plates. Yeah. So all the soot particles are removed. Okay. You have clean air, hot air going. Okay. And every once in a while, you shake this and clean it up. Yeah. So about 99% of these soot particles can be removed. And then you can have clean hot air going on. Now, this is slightly expensive process, so this had to be mandated. People didn't want to do it on their own. It costs about 1 to 2% of the electricity produced. Yeah. So that's $1 to $2 pennies out of your dollar profit. Well, 1 to 2 pennies out of your dollar revenue. Copier machines, xerographic copiers. Okay, so we'll learn how this thing is done. Photocopying, so there are photoconducting materials. What do you think those things mean? Don't read. I want you to figure it out.
Electric current to change color of the,
Light changes whether it conducts them.
That's right. Okay, so materials that'll be dark, insulators in the dark, and you expose them to light, they become conducting. So what's going on? How do they become conducting?
The heat from the light changes its properties. I don't know.
What do you need to make something a conductor?
free electrons.
Free electrons. So light is releasing electrons. Okay? So they become conducting. All right. So such materials are poor conductors in the dark, but become good conductors when exposed to light. Okay, so selenium is such a product. Is a photoconducting material. Okay, so what you do is you take a drum, 34, and coat it with selenium. Okay, and ionize the selenium so it's become positively charged. This is all done in the dark. Okay, so selenium is insulating, it won't lose its charge. And then here's something that you want to photocopy, you shine light on it. On the dark spot, that's still insulating, so it's not losing its charge. Whatever the selenium was exposed to light, that's become conducting, and that lost its charge because it was sitting on a metal drum, those selenium particles. Now, sprinkle the drum with a negatively charged toner, which will attract there. And then take a hot piece of paper and roll it over there. And the toner gets transferred to that. And you have a photocopy. Okay. Of course, a laser printer, what you're doing is, again, same thing. You've coated it with selenium. Instead of shining light like that in a laser printer, your laser beam is traveling like this, turning on and off. Yeah. Any of you guys have used an inkjet printer? No? So this is an interesting device. All right, so here are two metal plates. These are deflector plates. Okay, so if you have and the electric field is in this direction. Okay. If this particle is negatively charged, a negatively charged particle will deflect in the opposite direction of the electric field. Okay, so you can have a paint particle, charge it with electrons, and shoot it through this field, and it will deflect that. So here is the page on which you want to print. So you want to print something there, you make sure that you put enough charge so that it gets deflected there. That much. If you want to print something here, what do?
Don't alter it.
You don't give any charge.
Yeah.
Okay? And so you start off here. The left bottom portion is no charge. More charge. Okay. Input signals from a computer controls the charge given to each drop. Okay? How much so the more charge there is, the more charge it's reflected. So this is the bottom of the page. Drops are shot from generator G, about 100 drops per character. To print this S, you need 100 drops. Okay? So I told you about deflection like this. There's also plates deflecting in the horizontal direction. Okay, so that's what's doing that. And so what's your driver doing? Your printer driver, it's controlling the amount of charge on the drops. Okay. That's pretty amazing technology, and it's out the window now. You know. No longer. All right, so again, how does this proton repel this proton in Palm Coast? We said that this proton creates an electric field all around him, and the proton in New York or wherever is just responding to the local field. Okay? So now that's what we're going to talk about. So those are field forces. All charges will create electric fields around them. So this is this is the electric field around a combination of a proton and an electron. The field looks like this. Okay. And what you learn is if you put a positive charge there, it will move tangent to the field line. You put a negative charge, it will move in the opposite direction. Okay? So these guys don't know and don't care what is producing this electric field. These guys, all they're doing is responding to the electric field there. Okay? Okay, so here's a question for you guys. So here's this charge. Here's this charge in New York. Okay, what is it doing? It's feeling the field right here. Now what I'm going to do is I'm going to mess with him. I'm going to move this guy. When does he know?
Immediately.
What's that?
Immediately.
At the speed of light.
At the speed. Okay. So what happens is the change in electric field travels at the speed of light. And he'll know whatever. Probably 100th of a second later. So electric field lines begin at a positive charge and end on a negative charge. So field lines start on a positive charge, end on a negative charge. Fields in general are functions of time and space. So you see the electric field lines are different at different locations. So the electric field is a vector field. It's a function of position. How do we make it a function of time?
At a fourth dimension.
Jiggle this guy, and then it will become a function. Okay? So right now, we're not moving the charges, so all we're doing is just looking at these guys. Okay? Electric fields as a function of spatial coordinates. If the charges start moving, then the electric field will become a function of time as well. This is what is called a dipole. Two equal and opposite charges, okay? And this is a very important beast, and we'll talk about that. So this is how the field looks like around a dipole. And we'll measure this electric field in lab maybe next week, or we'll see. Maybe we can do it. Oh, today is what, Wednesday? Okay, we'll do it next week. All right, so this is how the field looks like. It's a dipole field. So here's how we indicate stronger fields. So let's say the field here is stronger and it's pointing in this direction. To convey that fact, all we do is draw a higher density of lines. The density of line indicates the strength of the field. Okay? And of course, the direction gives you the direction of the field. Okay. And this you can see naturally. Yeah. So here's a positive charge. The field lines radiate out like that. Okay, here the density of lines is higher than here. Okay. So here the field is stronger, here the field is weaker. All right, so let's say some charge distribution created these electric field lines. Okay. How do we detect these electric fields? How do we know there's an electric field in this room? How can you tell there's an electric field in this? So what you need is to detect an electric field, you need a charge particle. You place a charge particle. If the charge particle feels a force, then there's an electric field. Okay? We're ignoring the gravitational force. If there is no force on the charge particle, there's no electric field. All right, so now let me take one step back. What created the electric field?
The charge particle.
Charge particle created an electric field. So here's a beautiful symmetry. Charge particles create electric fields. And what do you need to detect those? Charge particle. Okay. So whatever is creating it is what you need to detect it. Okay. All right, so you put a positive charge particle, it feels a force in the same direction as the electric field. You put a negative charge, it feels a force in the opposite direction. Okay, so the force on a charge particle is the charge times the electric field there. And the electric field at a given point is defined as the force per unit charge. Okay. So charges move in the direction of, positive charges move in the direction of electric fields and negative charges move in the opposite direction. The units of electric field are Newton for force and Coulomb for the charge, so Newton per Coulomb. Yeah. So this is how the field looks like for for a positive charge, and this is the field about the negative charge. Okay. When you do spherical polar coordinates, you learn the unit radial vector, which is, if this is the origin, this is the unit radial vector. It's pointing away from the origin, and this is the unit radial vector. Okay. So the electric field is given by Q over R square. The electric field falls off as 1 over R square. If you're twice as far away, the electric field strength is 1/4 as strong. Okay? And it's always radially pointing outside. So from a positive charge, the field points away. From a negative charge, it's in the opposite direction of the unit vector. Okay. If you wanted to find the electric field at a point due to several charges, you find the electric field due to individual charges, and the electric field is a vector, so you just sum up the vectors. Okay. An electric dipole, this is an important thing. An electric dipole is two equal and opposite charges separated by a distance. All right, let's grab one of those 100 atoms. You can grab any one of them. What you'll find is, so we'll, for a concrete example, we'll grab lithium. Why do I keep grabbing lithium? because I can draw it in 2 seconds. All right. You grab any atom, what you find is, so here's the center of the positive charge. What does that mean? So if you have positive charges smeared evenly on a basketball, the center of positive charge is right at the center of the basketball. The center of negative charges, all these negative charges right on top of them. So for every atom, there is no dipole moment. Okay? The center of the positive charge is exactly on top of them. That's true for every atom. But let's say you start making molecules, that may no longer be true. Here's water. Here's the oxygen atom, here's the hydrogen atom, and the oxygen atom is greedy for electrons. So the electrons tend to be closer to the oxygen atom. So for this molecule, the center of negative charge is somewhere there, and the center of positive charge is somewhere there. Now, this fella has a permanent dipole moment. And this is extremely important. Okay. Why is this important? Okay, so let's say we'll make a molecule. Okay? And this molecule is, what we'll do is we'll give it a polar head. Okay, so we'll give it, this is the negative end of the head. And so you throw a bunch of these molecules in a cup of water, what will happen? All these guys will line up like this. Okay? So what ends up happening is, you take a bunch of these guys and throw them in a cup of water. What will happen is all the heads, what happened? So this is positively charged. So in the bilipid layer, okay, that end is positive. So this end is positive and this end is negative. So they'll line up like this. Okay. All right, so what this is extremely important. Let's go back to our bilipid layer. So you made a bunch of molecules like this, threw it in a glass of water, and they line up like this. Okay. Why do they line up like that?
Because the hydrophobic tails don't want to touch the water.
Okay. Hydrophobic, by the way, so that's sort of a bad term because they're not repelling water, they don't hate water. These guys are just attracted to water. So why this configuration? This is the minimum energy configuration. Okay, so you take a glass of water and they will form, if you have 100 of those atoms, they'll become a sphere like that. What if you have 1,000 of those molecules? Bigger sphere. This is inside, that is outside. Here you can do stuff, you can create life. Okay? So that dipole moment was extremely important. All right, so the dipole moment is denoted by P, and it's one of the charges times the distance, and it's a vector, and it's a vector pointing from the negative charge to the positive charge. The magnitude of the vector is given by that. So that's the dipole moment. Okay. And so you can create chambers using molecules that have a um, polar head and a neutral tail. Okay? So you could create chambers using those. And notice nothing is binding them. It's just electrostatic force that is holding them together. You can grab onto one of them and tug, and they'll come right apart. Okay. All right. The magnitude of the field from a point charge falls off as Q over R squared, as 1 over R squared. If you take a dipole, and we are giving you the field only there, the field at this point is the positive charge gives you a field in that direction, the negative charge field gives you a field in this direction, so they're working against each other. The net field there is weaker than that of a point charge. Okay? And it turns out that the field falls off as 1 over distance cubed. It falls off much faster. Okay? So if you're far away compared to this distance, it'll appear like a neutral particle. Okay. So the field will go off to zero much faster. All right, so here is a cloud of charge, and if you wanted to find the field at this point, what you do is you find the field due to this guy. The field due to this piece is k dq by r squared. R hat is a vector in this direction. And then what you would do is, if you wanted to find the field due to the entire cloud, you'd break it up into little pieces and add the field due to all of them. So you're adding a bunch of vectors that are pointing in every direction. Okay? That would be a three-dimensional integral, and that would be hard to do. Okay, so you'd be able to do it in very special cases. So that's the field. That's how you would calculate the field at a point due to a distribution of charge. And then if you want to find the field here, what do you have to do? Another impossible to do integral. How about here? So you have an infinitely many impossible to do integrals. Okay? So in the next chapter, we'll see how to calculate electric fields due to distributions of charges. And you'll be able to calculate electric field for very, very symmetric distributions of charges. Okay? And that's Gauss's law. All right, so in preparation for that, we'll define charge densities. Okay, so this is volume charge density. So let's say you take a bunch of charges and smear it evenly in a volume. Okay, the charge density is given by the charge divided by that volume. Surface charge density, you take a bunch of charges and smear evenly on an area. This is the surface charge density, sigma. Line charge density, you take a bunch of charges and smear evenly on a length of wire. Okay, so that's linear charge density, lambda. Okay, so let's say you take a ring and smear it evenly with charges. What we're going to give you is, so essentially, somebody has done this integral for you for this charge distribution. What we're going to give you is an expression for the electric field along the axial points. We can't give you the electric field anywhere here, in very specific locations. that integral can be done. Okay. And I'm not even going to do the integral, but I'm just going to point out. Okay. So the electric field due to this guy is pointing in this direction. That has an x component and a perpendicular component. The electric field due to this guy is exactly in the opposite direction. And this perpendicular component cancel, only the axial components add up. So the electric field due to this guy and the electric field due to this guy are reinforcing in the same direction. And so you can do that for the entire ring. And the electric field, so you take a ring and charge it, and what we're giving you is the electric field along axial points. Is there an electric field here?
Yeah.
Yeah. We just don't have an expression. Okay. So we are not giving you electric fields in infinitely many points. We are only giving you electric fields at this point, okay, at these points. And there's the expression for the electric field. Kx, Q is the total charge on the ring. X divided by x squared plus a squared to the power of 3 halves. Okay. So this is x squared's root is, that's x to the power 1 cubed, and then this cancels with x. So it's the electric field is 1 over length squared. Okay. Well, we gave you the electric field due to a ring along the axis. Okay, what about if we have a disk and we smear this evenly with charge? You think you could find the electric field due to this guy? And again, all we're asking you is to find the electric field along the axis. We're not asking you to find it there because we know we can't do that. We can't have a closed form expression. So here's the little trick. Okay? This is what calculus teaches you. Once you know this, all you do is break the disk into rings, concentric rings. You know the electric field due to this ring, then the next ring, and just add up the electric fields due to the rings. Okay? And that's what this is doing. And here is the expression. So the electric field on an axial point is given by 2 pi sigma. What is sigma?
The surface, charge of the city.
Yeah, the charge per unit area on this surface. Okay? And K is the Coulomb constant. Z is the distance along the axis from the disk, and R is the radius of the disk. So now we have the electric field along the axis from a disk. Okay, next thing what we'll do is the following. Let's make the disk bigger and bigger. What's happening when you're making the disk bigger and bigger? At the same point, we'll keep Z the same.
The field gets bigger because 1 minus gets smaller.
See, he's a smart fellow. So you're making bigger and bigger disk. The charges, you're getting more and more charges. Okay, but look at this. You would think that the field gets bigger and bigger. Okay, but let's make R going to infinity. This goes to 0. The field has become constant. Mind-blowing. So from an infinite sheet, the field from an infinite sheet is that. Doesn't depend on distance. It's sigma by 2 epsilon naught. So let's say you have an infinitely charged sheet, evenly charged sheet. The field here is sigma by 2 epsilon naught. The field in New York is sigma by 2 epsilon naught. The field in the next galaxy is sigma by 2 epsilon naught. So, from this sheet, the field in this half of the universe is sigma by 2 epsilon naught, and the field in this half of the universe is exactly the same. Yeah. All right, so the units for fields were Newton per Coulomb. And in Faraday atmosphere, there's a field of 100 Newton per Coulomb pointing down. So there's you can walk outside and there's an electric field of, okay. And you will learn in the next chapter, this is volt per meter. So go outside and there's 100 volts for every meter. Okay. Do you guys know how lightning happens?
Different charge in the ground versus the cloud.
Okay, yeah, so we'll figure it out. So to have a spark in the air, that's lightning, what you need is an electric field of more than 3 million volt per meter, or 3 million Newton per Coulomb. Okay, so here's what happens. Like our friend said, so let's say here's a cloud, there's charge separation. Again, I'm just making up stuff. Yeah, so we'll make this positive. Okay. So there's an electric field in this direction. Here are all these atoms, atmospheric atoms, and they're all neutral. What are these guys? Molecules. They're nitrogen and oxygen molecules. Okay. Now let's say there's a stray electron in the atmosphere. What does this electric field do?
Pushes it to the ground.
Well,
Or, sorry, it tries to the cloud.
yeah, so it moves in this direction. Okay. So the electron moves in this direction, it accelerates in that direction, there's a force in that direction, and pretty soon it collides with one of these guys, and loses all its energy. So nothing happens. What happens if I increase the strength of the electric field?
It'll collide with more acceleration, with more force.
More force. Okay, so let's say it travels a certain distance between collisions, and if you increase the electric field in that distance, okay, its final velocity will be greater. Here is an equation from the past. So you start off at rest. For a given distance, the greater the acceleration, greater your velocity. Okay. Now, if this field becomes greater than 3 million volts per meter, that is, if the electric field is such that for every meter there's 3 million volts, these electrons between collisions will gain enough velocity where they start knocking off electrons from these guys. What has become of this atmosphere now?
Negatively charged.
This atmosphere that was neutral has suddenly become a copper wire. Okay? And this cloud discharges through this copper wire. That large electric current flowing through there, heats up the atmosphere and expands, and that's the thunder you hear. And what is the lightning? What is the light? All the electrons recombining emit light. Okay, so when the electric field becomes greater than that, the charges between collisions gain enough speed to knock at other electrons off. Okay, and you make the atmosphere conducting. So that's what that is. So every time you see a spark, that's what happened. Is there any place where you experience that?
Metal current?
Huh?
Metal current?
Every time you drive your car, that spark plug is creating lightning to light your gas. Okay, so what do you need for lightning? 3 million volts per meter. So if the spark gap is a millimeter, all you need is 3,000 volts. Okay. All right, so here's a way to create a uniform electric field. You can smear this wall with positive charges, evenly smear that wall with negative charges, and you learn about these as capacitors. Okay, you can create an electric field like that, uniform electric field. If you put a positive charge there, it'll accelerate towards there. So the force on a positive charge is, the force on a charge is Q times E, which is equal to mass times acceleration. Okay, here is a electric field. You shoot a negative charge like this, the negative charge in a uniform field will feel a uniform force in this direction and will be deflected like that. Okay, this guy, what does he feel? This mass? Gravity. How about here? Is the force changing? No, this is a uniform force. What is the trajectory of this guy?
Parabolic.
Parabolic. What is the trajectory of this guy? There you go. All right. So that's how they deflect. Okay. So these are CRT tubes. Here's an electron beam. These are deflecting plates. This is for vertical deflection, horizontal deflection, and you can hit phosphorescent coating there, so you can light up this thing. Okay. And so the old time TVs drew pictures on there, and so that beam was scanning the screen, and so that you see a smooth motion, what do you have to do?
Fire a lot of electrons.
You have to draw that picture 30 times a second. So that beam was scanning the whole screen 30 times a second. More than that. Okay? All right, now we'll talk about something that you use in your everyday life. So again, this water molecule has a dipole moment. What is happening? These guys, the oxygen, I'm exaggerating this, but for this molecule, the center of negative charge is there somewhere, and the center of positive charge is there. Okay? And this is important. All right, so you have an electric field like this. You have an electric field like this, and if you put a positive charge, the positive charge feels a force in this direction, and the negative charge feels a force in this direction. Okay, I'm going to draw a water molecule. Again, this is not to scale, but okay. So I'm going to put a water molecule like this in the electric field. What will happen? This guy will feel a force in this direction. This negative charge, the charges are equal, will feel an equal and opposite force in this direction. Okay? So the water molecule, there's the electric field, will turn like that. It will align towards the electric field. Okay? Let's be mean. Now we'll flip the electric field. What will happen now? It will go in the other direction. We'll be mean again. Flip the electric field. Let's flip the electric field 5 billion times. That's what your microwave will do. Okay? So the microwave frequencies are about 5 billion. You're grabbing onto a water molecule and jiggling it. What did you do?
Produce heat.
I'm sorry?
Produce heat.
You dumped energy into that by doing work on it. You heated the water molecule, and then the water molecule heats the surrounding food. Yeah. So the torque on the water molecule is P, the dipole moment crosses with E, which is making the water molecule spin. Okay. The torque tends to align the dipoles with the electric field. Okay. So this guy had potential energy, got converted to kinetic energy, just like that. If you put a dipole in an electric field, it has potential energy which can be converted to kinetic energy. Okay, so the potential energy that of the dipole is P dot E. Okay, and the potential energy is minimum when it's aligned with the field. So when the dipole is aligned with the field, the potential energy is minimum. All right, guys. So I'm sorry we had to rush